Hello. In the previous episode, we introduced group theory, conservation laws, molecular symmetry, and point groups. And if you happen to have missed that episode, you should go and watch that first before coming back to this one. Today we shall talk about character tables, the great orthogonality theorem, and selection rules for spectroscopy. But let us start with a couple of theorems. We know that the trace of a matrix A is given by the sum of the diagonal elements, that is sigma I, aii. The product of two matrices A and B can be written as sigma k, aik, bkj. So the first theorem is that the trace of the product AB is the same as the trace of the product BA. To prove this, we note that the trace of the product AB is sigma I, sigma k, aik, bki, and the trace of the product BA is sigma k, sigma I, bki, aik, but aik and bki are just numbers, so we can interchange their order and write sigma I, sigma k, aik, bki, which we recognize is the same as the trace of the product AB. The second theorem is that conjugate matrices have identical character. Now, if you recall, if matrices A and B satisfy this equation, B equals x inverse AX for any element of the group X, then A or B are said to be, A and B are said to be conjugate to each other. Thus, the trace of B is the trace of x inverse AX, which is the trace of x inverse A times X, which by the previous theorem is equal to the trace of x times x inverse A, but x times x inverse is just the identity, and so this is just the trace of A. Thus, the trace of B is equal to the trace of A, or conjugate matrices have identical character. We shall use this in future to group different symmetry operations into classes and arrange them into a character table. So this brings us to the great orthogonality theorem, which can be written in this rather complicated form, where the sum over R is the sum over the symmetry elements, and it runs over all the symmetry elements in the group. I and J are representations, and these can be either reducible or irreducible representations. We will define these later. Gamma I of R is the matrix for the symmetry operation R in the representation I. Li and Lj are the dimensions of the representations I and J, and delta Ij is the Kronecker delta. H is the order of the group. The great orthogonality theorem is actually several different theorems combined into one compact mathematical statement, as we will see. To take an example of a reducible representation, consider the point group C2V, which we discussed in the previous episode. The identity matrix is given by 1, 0, 0, 0, 1, 0, 0, 0, 1. C2Z is given by minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. The trace of the identity is 3. The trace of C2 is minus 1. Sigma Vxz is given by 1, 0, 0, 0, minus 1, 0, 0, 0, 1, and sigma V dash Yz by minus 1, 0, 0, 0, 1, 0, 0, 0, 1. The traces of both these reflections are 1. This gives a reducible representation, which we call gamma, with traces identity 3, C2 minus 1, sigma V and sigma V dash 1 each. Note that all these matrices are 3 by 3 matrices, so this is a three-dimensional reducible representation. The dimension of a representation is always given by the trace of the identity matrix. As another example, consider the matrix representation for the point group C3V, which we also discussed in the previous episode. The identity is again given by this matrix with trace equal to 3. Sigma V xz is given by this matrix again with trace equal to 1. C3 and C3 squared are given by these matrices, both of which have trace equal to 0. Thus, this gives us a three-dimensional reducible representation gamma with traces identity equal to 3. C3 and C3 squared, which belong to the same class, have trace equal to 0. And the three reflections belong to one class and have the trace equal to 1. Although we didn't develop the matrices for the other two reflections, since all three reflections belong to the same class, by the theorem we just proved, they have the same character. With that, let us now return to the great orthogonality theorem and its corollaries. The first corollary is that the sum of the squares of the dimensions of the irreducible representations is equal to the order of the group. Thus, sigma I Li squared is equal to H, the order of the group. The sum of the squares of the characters in any irreducible representation is equal to the order of the group. That is, sigma R chi I of R squared is equal to H. The vector whose components are the characters of two different irreducible representations are orthogonal. That is, sigma R chi I of R times chi j of R, where I and j are two different irreducible representations. This is equal to 0. Okay? That's the orthogonality. In any given representation, reducible or irreducible, the characters of all matrices belonging to operations in the same class are the same. And the number of irreducible representations is equal to the number of classes in the group. Okay? So we can form the irreducible representations once we know the classes in the group. With that, let us return to the point group C2V and construct the character table for it, which is the table of characters of the irreducible representations. First of all, we recall that C2V is an abelian group. That is, every symmetry element commutes with every other symmetry element, which implies, from the theorem we introduced in the previous episode, that every element is in a class by itself. Therefore, there are 4 classes, since the order of the group is 4. And which means there are also 4 irreducible representations, since we just showed from the corollary of the great orthogonality theorem that the number of classes is equal to the number of irreducible representations. And these 4 irreducible representations are mutually orthogonal. And the sum of the squares of the dimensions of the irreducible representations is equal to 4, the order of the group, again from the great orthogonality theorem. So there are 4 irreducible representations, and the sum of the squares of their dimensions is equal to 4, which means that each irreducible representation has to have dimension 1. And finally, the sum of the squares of the characters of each irreducible representation is also equal to 4, the order of the group. With that, we can conclude that the character table for C2V has to have this form. There are 4 mutually orthogonal, one-dimensional, irreducible representations. And the reducible representation gamma that we constructed earlier has characters 3, -1, 1, and 1. And so we can easily verify that gamma is equal to A1 plus B1 plus B2. Likewise, we can construct the character table for C3V. C3V consists of 3 classes I, 2C3, and 3 sigma V. Therefore, it has to have 3 mutually orthogonal irreducible representations, and the squares of the dimensions of these irreducible representations has to add up to 6, the order of the group. A, B are common notations for one-dimensional irreducible representations, whereas two-dimensional irreducible representations are denoted by E. And we can easily verify that these irreducible representations are orthogonal by multiplying 1 times 1 plus twice 1 times 1 plus 3 times 1 times minus 1 is equal to 0. 1 times 2 plus twice 1 times minus 1 plus 3 times minus 1 times 0 is equal to 0, etc. The irreducible representation gamma that we introduced has characters 3, 0 and 1. So it is easy to verify that gamma is equal to A1 plus E. Now let us introduce the direct product. The characters of the direct product of two irreducible representations are equal to the products of the characters of the irreducible representations. With that, we can construct the direct products of all the irreducible representations of C2V, and the direct product is represented by this cross symbol. The first irreducible representation, that is A1, which has characters all 1, 1, 1, 1, that is all positive characters. This is known as the totally symmetric irreducible representation. And we can see that the direct product of two irreducible representations, gamma A and gamma B, will contain the totally symmetric irreducible representation only if gamma A equal to gamma B. That means the direct product is equal to A1 only if we are multiplying an irreducible representation with itself, like in here A2 times A2. Similarly here B1 times B1 will give us A1, and likewise B2 times B2 gives A1. No other direct product will give me the totally symmetric irreducible representation. We can now talk about normal modes of vibration in a molecule. Each normal mode behaves as a harmonic oscillator. A normal mode is a concerted motion of many atoms. Translations and center of mass rotations have been separated out, so a normal mode does not translate or rotate the molecule. All atoms involved in a normal mode pass simultaneously through their equilibrium positions. Normal modes are independent, they form an orthonormal set. Any atomic displacement can be decomposed as a combination of x, y and z Cartesian displacements of the atoms. If we do this for water, we have this matrix whose trace is 9. Similarly, for the C2Z rotation, which is the rotation through 180 degrees about the z-axis, that is the axis passing through the oxygen, that leaves the z displacement vector on oxygen unchanged, but it flips the x displacement vector to minus x on oxygen. So x to minus x. And similarly, it flips y, which is the vector pointing out of the screen, to minus y, which is a vector pointing into the screen. As far as x1 and x2 are concerned, since the C2 operation moves hydrogen atom 1 to the position of hydrogen atom 2 and moves hydrogen atom 2 to the position of hydrogen atom 1, x1 goes to minus x2 and x2 goes to minus x1. z1 goes to z2 and z2 goes to z1. y1 goes to minus y2 and y2 goes to minus y1. So we have this matrix which has the character equal to minus 1. It is -1 plus -1 plus 1 is equal to -1. Note that any atom that moves under a symmetry operation does not contribute to its character. So here the atoms hydrogen 1 and hydrogen 2 move under the symmetry operation C2. Oxygen alone is unmoved, and therefore hydrogen atom 1 and hydrogen atom 2 do not contribute to the trace or the character. Only the oxygen atom contributes to the character. Sigma Vxz is reflection in the plane of the screen. It leaves the x and z coordinates of all the atoms unchanged, but it flips the y to -y on each atom, and so we have this matrix yo going to -yo, y1 going to -y1, y2 going to -y2, so that the trace is equal to 3. Again, sigma vyz leaves the z vector on oxygen and the y vector on oxygen unchanged, and flips x oxygen to -x oxygen. It transforms x2 to -x1, x1 to -x2, z1 to z2, z2 to z1, y1 to y2, and y2 to y1, so that we have this matrix which has a trace equal to 1. Again, we note that any atom that moves under a symmetry operation, here H1 and H2, does not contribute to its character, so we can consider just the oxygen atom in calculating the trace. So the reducible representation for the normal modes of water has the characters 9, -1, 3, and 1, and we can verify that this gamma is equal to 3a1 plus a2 plus 3b1 plus 2b2. The formal way to obtain this is by using the great orthogonality theorem. Now, the Z translation transforms as A1, X translation transforms as B1, and Y translation transforms as B2. Rotation around Z transforms as A2, rotation around X transforms as B2, and rotation around Y transforms as B1. So we have the three translations will take away one A1, one B1, and one B2, and the three rotations will take away the A2 and another B1 and another B2. So subtracting out the translations and rotations, we are left with gamma vibration is equal to 2A1 plus B1. So the symmetries of the three normal modes of vibration of water are nu1, which belongs to symmetry A1, is the symmetric stretch where both the OH bonds are stretching or compressing at the same time. Nu2, which belongs to symmetry B1, is the asymmetric stretch where one bond is stretching while the other is compressing. And nu3, which also belongs to symmetry A1, is the bending coordinate. All three normal modes, as we shall see, are allowed under both infrared and Raman. So the OH symmetric stretch, which belongs to A1, has a frequency of 3657 centimeter inverse. The OH asymmetric stretch, which belongs to B1, has a frequency of 3756 centimeter inverse, and the HOH bend, which belongs to A1 again, has a frequency of 1595 centimeter inverse. Here are the experimental infrared spectra of ice and liquid water. Here's the 1595 centimeter inverse line, and here are the 3657 and 3756 centimeter inverse lines. We can identify these same transitions in the infrared spectrum of water on zinc selenide. This is the bending or the scissoring mode, and here are the two stretches, the symmetric and asymmetric stretches, and this is a combination band. How do we know all these transitions are symmetry allowed? Well, for that we shall use group theory and quantum mechanics. For infrared, the interaction Hamiltonian in the dipole approximation is H dash equals mu dot E, where E is the electric field of the radiation and mu equals ER is the electric dipole moment of the molecule. If the transition integral, that is the integral psi f mu psi I d tau is equal to 0, then the transition psi I to psi f is forbidden. But if the transition integral, that is the integral psi f mu psi I d tau is not equal to 0, then the transition psi I to psi f is allowed. In the dipole approximation, an infrared transition between two states is allowed if the direct product of the representations of the initial and final states is or contains the irreducible representation to which the dipole moment belongs, that is, to which x, y, or z belongs. Integral psi f mu psi I d tau is not equal to 0 if the direct product of psi f and times mu times psi I contains the totally symmetric representation A1. That is, if x or y or z belongs to the same irreducible representation as the direct product of this psi f times psi I, then the transition from psi I to psi f is allowed. Integral psi f mu psi I d tau is equal to 0 if the direct product of psi f times mu times psi I does not contain A1, the totally symmetric representation. Then the integral will go to 0. That is, if x or y or z does not belong to the same irreducible representation as the direct product of psi f and psi I, then the transition from psi I to psi f is forbidden. Nu1, which is the symmetric stretch belonging to A1, is allowed because the integral bra psi nu1 z psi 0 ket is equal to the integral of the direct product of A1 times z, which is also A1, times psi 0, which is also A1 d tau, which is equal to integral A1 d tau, which is not equal to 0. Likewise, nu3, which is the bend belonging to A1, is also allowed because the integral bra psi nu3 z psi 0 ket is equal to the integral of the direct product of A1 times z, which is also A1, times psi 0, which is also A1 d tau, which is equal to integral A1 d tau, which is not equal to 0. And likewise, nu2, which is the asymmetric stretch belonging to B1, is allowed because the integral bra psi nu2 x psi 0 ket is equal to the integral of the direct product of B1 times x, which is also B1, times psi 0, which is A1 d tau, which is equal to A1 integral A1 d tau, since B1 times B1 is A1, which is not equal to 0 upon integration. Thus, all three modes are allowed for infrared. For Raman, the interaction Hamiltonian H dash is E dot alpha dot E, where E is the electric field of the radiation and alpha is the polarizability tensor with diagonal elements alpha xx, alpha yy, and alpha zz, and off-diagonal components alpha xy, alpha yz, and alpha xz. A normal mode will be Raman active if it belongs to the same irreducible representation as one or more of the components of the polarizability tensor of the molecule. If integral psi f alpha psi I d tau is equal to 0, the Raman transition from psi I to psi f is forbidden. If the integral psi f alpha psi I d tau is not equal to 0, the Raman transition from psi I to psi f is allowed. A Raman transition from one state to another is allowed only if the molecular polarizability of those states is different. Nu1, which is the symmetric stretch belonging to A1, is allowed because each of the three integrals, bra psi nu1, x squared or y squared or z squared, psi 0 ket, belongs to the direct product of A1 times A1 times A1, which is the integral of A1 d tau, which is not equal to 0. Likewise, nu3, the bend belonging to A1, is allowed again because each of the three integrals bra psi nu3, x squared or y squared or z squared, psi 0 ket, belongs to A1 times A1 times A1 d tau, which is the integral of A1 d tau, which is not equal to 0. Nu2, the asymmetric stretch belonging to B1, is allowed because the integral bra psi nu2 xz psi 0 ket is equal to B1 times xz, which is again B1 times A1. B1 times B1 gives A1 and A1 times A1 gives A1. So this is integral A1 d tau, which is not equal to 0. Thus all three modes are allowed for Raman. Here we see the Raman spectrum of water. The bending mode appears here, while the symmetric and asymmetric stretch appear here. We shall stop here for today, and next time I will complete our exploration of group theory and quantum mechanics with a discussion of Lie groups.